me a favor and solve for n sub t here and solve for n sub a here? Can you do that for me? What do you got? P sub t times the unique volume over
RT.
the ideal gas constant and the unique temperature. Because that temperature belongs to the mixture, is that right?
Mm-hmm.
So can you do that for me here? P sub A, the unique volume over R and T. Is that fair? That's true, isn't it? Okay. Allow me just one more. Allow me just one more. Can you do me a favor and put this mess up there and this one down here? Can you do that for me? N sub A, what's N sub A? B sub A times B, R and T, right? And what do you got down here? B sub T, V over R and T. Oh, I think one of that got
RT.
Woo! Yeah. Cancellation party. My favorite. So what's up?
P over
P sub A over
P sub T.
B sub T. I don't know about you, I get goosebumps. I don't know about you. Dalton's law of partial pressures. The mole fraction of an individual component is equal to the partial pressure of that component over the total pressure of that component. Or the total pressure of the mixture. I don't know about you, I get goosebumps. Isn't that what we said? There.
Yeah.
We said that the contribution of the pressure of A to the total pressure was going to depend on what? On how much of A is in there. How do you measure the presence of a gas in a mixture? Mole fraction. How much of A is in the mixture? The more A in the mixture, the higher the contribution to the total. I'm sure Dalton did exactly that when he derived it. I'm sure. That's Dalton's law. What you end up memorizing, what everybody and their brother memorizes is this for Dalton's law. That the mole fraction of a component is related to its partial pressure. Of course it is. The higher the mole fraction, the higher the contribution of that particular item to the total pressure. Of course it is. We good? Mm-hmm. Okay. All right. Let's go back to this. Let's go back to this one. You have everything, right?
Yeah.
So I can lose one. What if I have B sub T and I want the P of a gas collected over water?
P gas.
I want the P of a gas collected over water. What if I have a total pressure and I want the pressure of a gas collected over water? Isn't it true inside of that container that P sub T is equal to P of the gas plus
P of
P of water? That's Dalton's law. That the individual components of a mixture of a gas are going to contribute towards its total pressure. And that individual composition, the individual contribution, the individual gases are called partial. Of course, because they're part of a whole. So if I wanted just the pressure of the gas, what would I have to do?
Subtract the pressure of the P, the TL minus piece of water.
Subtract the pressure of the water. You know what that's universally called? Drawing the gas on paper. Yep. You remember your wet gas that was collected over water? You just dried it. And if you do problems that are collected over water and they tell you they collected a wet gas and you ignore it, you're going to get all the problems wrong because you're forgetting to subtract the vapor pressure of water. We good? So, where do I get vapor pressure of water? On tables. They're like boiling points and melting points. They're in the back of your lab manual. They have to be given in the problem. They have to be given on the test because no one memorizes tables of vapor pressure. In fact, I have an app for that. Vapor pressure. You think I'm kidding? I have my periodic table. I have everything here. There's an app for that. Look it up and get busy with those vapor pressures so you have them with you as fast as possible so you don't have to be flipping through pages of a book. Vapor pressures of water. Vapor pressures of water at different temperatures. It's a table. You just look it up. These come from a table. Where do the vapor pressures of water come from? And when you have a gas collected over water and you need its pressure, what are you going to do? Take the total pressure and subtract the water. Is that good? Dalton's law in operation. We good? Okay. Let's do some problems. Let's do some problems. And let's do little concept diagram. Little concept diagram. The pressure of A. Let me put it. The pressure of gas A. I now have a brand spanking new way of finding it. If I have composition, did you notice that shining example of something glaringly missing from these stories is the temperature and the volume? We canceled it out. So when the story doesn't contain volume and temperature, there's always Dalton's law. Because for everything else, you got PV equals nRT. And now you have two different ways of finding the pressure of a gas. Are we in agreement? The thing is that for PV equals nRT to work, what do you absolutely have to have access to? Temperature and volume. If you don't, if all you have is amounts, what do? Dalton's law. And you're going to get the same answer. So the pressure of a gas can be found from composition and Dalton's law, or from ideal gas behavior assumption and PV equals nRT. But PV equals nRT absolutely assumes that you have access to the temperature, pressure, volume of a gas. Treat it always as an algebraic equation. If they want to ask you for pressure, you absolutely need to have what? Everything else. Otherwise you can't do the problem. It's just a regular algebra problem. Everybody okay so far? You sure? Okay. So, how about this? How about at a total pressure of 800 torr. Gosh, I don't want to read this. Well, I read this. At a total pressure of 800 torr, so P sub T is equal to 800, and a total pressure of 800 torr, I have 0.20 moles of helium and 2.4 grams of methane. Find find the partial pressure of methane, find the partial pressure of helium. Take your time. Tell me what to do.
Is that CH4?
CH4. At a total pressure of 800 torr, you've got 0.20 moles of helium and 2.4 grams of CH4. Grams of methane. CH4. CH4. What are you gonna do?
Change the gram. I have to make grams small.
Yeah, do the mole fraction. Why?
You don't have
What are my two options? Either I go with PV equals nRT, or I go with Dalton's law. Do I have enough information for PV equals nRT?
No.
Nope. So I'm going with Dalton's law. Dalton's law for when you don't have temperature and volume, because for everything else, there's PV equals nRT. Okay? So, what are you gonna do?
You have to convert.
You gotta tell me what to write. Tell me what to do.
Big X.
Big X of what? Of methane. Okay. So mole fraction of methane is equal to?
The total is 800. That goes in the bottom.
Okay.
800 yeah. But you have to convert. You have to convert to 0.4 to.
No, I agree with him. Right? I do. He's right. He's right. And so is this, right? Is equal to the partial pressure of helium divided by 800. I agree. And then later on, you're going to tell me if there's two ways of doing this from this point. Yes. What's my X? That's my X. Uh-huh. What are you going to do? Convert those grams to moles in a hurry, because otherwise I'm never going to get that mole fraction. So what do you want to do?
2.4.
2.4 grams of CH4 times, I may be totally clueless, but I know it goes down here. 16 grams of CH4. And that is 1 mole of CH4. And that's how many moles? 2 and change divided by 16. How much?
0.15.
0.15. And what's after the 5? Nothing? So, okay. Well, we use 2 sig figs, so we should be respectful of the sig figs. So now I know what the mole fraction of methane is. So that's 0.15. Can you now tell me what the partial pressure of methane is? You're already taking too long.
120.
How much?
120.
Did everybody get 120? Why are you staring at me? I have no idea what it is that you're doing. Get a calculator and hurry up. Test 3 is like in 3 weeks, y'all. 120. 120 what? What are these? We're working in torrs. We're working in torrs. Are we good? Okay.
Wait.
How do you?
Oh, hold on. We haven't done the mole fraction. This is just moles. Moles of CH4. Moles of CH4. We gotta put the mole fraction. This has to be mole fraction. This has to be mole fraction. That has to be mole fraction. We just found the moles of methane. What's the mole fraction?
0.15 over.
Everybody needs to have a calculator. How do you calculate mole fraction?
Here's the partial with the total.
How do you define mole fraction?
Moles over
The moles, look at your notes.
total moles and mixture.
The moles of each component divided by what?
The total moles.
The total moles in the mixture. You gotta do mole fraction first. That 0.15, what is that?
Moles of
Moles of methane. So what's a mole fraction of methane?
0.1.
0.15 divided by 0.2.
0.15 divided by what?
0.35.
35.
0.2.
0.15 divided by what?
135.
Which you got by doing what?
Adding the moles.
0.15 plus
120.
0.2.
Yeah.
And now, what's the partial pressure of methane? What's the partial pressure of methane? You guys are taking too long already. How much is it?
143. 143.
Okay, let's go back to this. Let's go back to this. How much is 0.15 divided by 0.35?
0.428.
0.428.
This is equal to what?
428.
0.428. Now solve for the pressure of methane.
342.
Somebody second that.
342.
And what units are these? Scores. A while back, I mentioned a second way of doing this problem. If I wanted to do the partial pressure of helium, what would you do? If I wanted the partial pressure of helium, now,
Subtract 800 minus.
I would just subtract from 800.
800 minus.
Because in a multi-component mixture, the total pressure is equal to the addition of the individual pressures. And if you already know this one is 342, how much is the other one? 800 minus 342, which is how much?
458.
Keep that number in mind. And let's compare it to if you do it the long way. Here we go. Let's do it the long way. Repeat the process. How much was it? What was it? 458? 358?
458.
458.
Go for it. How much is the mole fraction of helium? How much is the mole fraction of helium?
0.2.
0.571.
Right, but show me the calculation of mole fraction.
0.2.
0.2 moles over the total moles. And the total moles is 0.15 plus 0.2.
571.
And how much is that?
0.571.
0.571.
571.
Just a quick check. How much do these two have to add up to be? One, do they? Yeah, 99999. Right, because they have to. So what's another way of very quickly getting mole fractions of a two-component mixture?
1 minus.
And once I had this mole fraction, what do?
Subtract it from 1.
Subtract the moles. And you're going to get the other mole fraction. We good?
What was the point of the 122 that you were looking for?
No, the 120 is when we put just the moles here. They can't be moles. This has to be mole fraction. This big capital letter X is what? Say mole fraction. What's mole fraction? The moles of each individual divided by what? Total moles. You have it in your notes. Mole fraction. Mole fraction.
I still don't get it.
The 120 you get if you put 0.15 here. If you put this number, if you put 0.15, if you put 0.15 here and solve for this, you get 120. But the question is, what goes here? Individual moles or mole fraction? What goes